Welcome back, and last video we covered vector functions, so position vectors as functions of time, and now in this video we're going to cover vector calculus, which is really the guts of this topic, and it's really not that hard. If you're okay with differentiation and anti-differentiation, then this is really no more stretch, just a bit more. It's not harder, it's just involves a bit more. You need to just make your writing really neat and keep everything organised. So here we go. So at the moment, well, let's just go back. Want to go back a step. If you remember that we had x in kinematics, we talked about x as position. Let's write down position. And what happened is that I'm just going to get rid of position. It's going to annoy me. X is our position. And what we could do is we could differentiate x with respect to time. Okay, so I'm just going to say d dt. We're going to differentiate that with respect to time, and we end up with dx dt, which is velocity. That's our velocity. Velocity is the change of position with respect to time. And then also from there we could take the derivative again, and we end up with dv dt, which is acceleration. So that's our little pattern there. We start with position, we take a derivative, we end up with velocity. We take the derivative again, we end up with acceleration. And we could also go back the other way. If we start with acceleration and come back in this direction, we can take the integral with respect to t, and what do we get? We get velocity. If we start with velocity and we want to go back in this direction, if again we take the integral with respect to t, we end up with position. And so this is the order of things. This is how everything works together in functions of time. We've got position, velocity and acceleration all working hand in hand, and you need to know how to change between each one. What we're going to do today is something very similar. Is that we're going to have a position vector rt that tells us a position with respect to time. Now, if we differentiate that, just like before, then we end up with what we call r dot of t, which is just the derivative of the position function, the first derivative. One dot means the first derivative, and that essentially is our velocity function. Velocity and time. So I'll just put a tilde on it because it's a vector. Again, if we differentiate again, then we end up with r double dot of t, which is the second derivative of our position vector, and that's like the acceleration. It is the acceleration, but it's just written as r double dot. You can write it as acceleration. It's in most of your exams it'll be written r double dot. And again, you can go backwards in this direction, take the antiderivative with respect to t, and again you can do it the antiderivative with respect to t to come back in the opposite direction. And so that's what we're going to be covering in this particular video. And that's basically it. Let's just crack on into some examples. I hear you say. So let's look at this. Find r dot of t, that's a dot, and r double dot t. Awesome. If, I better give you an RT, our position vector is equal to half ti plus t squared j. So there's my vector function as a function of time. Let's go. Here we go. So how do we take the derivative of a vector? So I'll show you right now. All we need to do is take the derivative of each of the parts. Okay, so the derivative of r, so the first derivative, is equal to, what we do is we take the derivative of this first part. Now, what's the derivative of half t with respect to t? That's just equal to half. And so we're just taking the derivative of each of the components. Plus, what's the derivative of t squared? Derivative of t squared with respect to t is 2t. And that's in the j direction. And it's as simple as that. There's your r dot of t. Remember, this gives you an idea of what the velocity is. the velocity with respect to time. So the velocity is constant in the I direction, but it's increasing in the j direction. Okay, let's do r double dot. R double dot of t is equal to, now we'll take the derivative again. What's the derivative of half? That's 0. I'll just write it for now, but I won't write it next time. 0i, so that just disappears. There is no I component of r double dot. Derivative of 2t is just simply 2. And so you're left with just 2j. That's my acceleration function, if you like. What does that tell us? It tells us that there's constant acceleration in the upwards. If j is upward, which it normally is, that tells you it's constantly accelerating in an upwards manner. So I don't know what might do that. A rocket or something like that might have constant acceleration in an upwards motion. So of 2 meters per second squared, if that were a unit sort of thing. Okay, so that's how to do it. All you do is you take the derivative of each of the parts in there. And it's as simple as that. Let's do one in the opposite direction. Let's do one where you start with something else. So let's go r double dot of t is equal to sine 2t I minus cos half t j, and we're also told that r dot of 0 equals negative half I, and also that r of 0, no dot, is equal to 4j. Okay, so let's do this question. You might be wondering, why have we been given initial conditions? And you'll soon find out. And you probably guessed why anyway, because what happens when you integrate? You get constants, and so we're going to need to do that. Okay, so we've got r double dot. What we want first is r single dot. Sorry, the question wants us to find rt. I haven't written it there. That's what we're going to do. So a little bit lazy. R single dot t. What we need to do is integrate each of the components. Okay, so let's do that. What happens when we integrate sine? Well, sine will go to negative cos, so it'll be negative cos 2t I, and also this 2 we need to divide by that 2, so there'll be a half in there. Okay, so there's the derivative of the, the antiderivative of the first part, or is it? Now I've written I there. Just, whoops, I'll take that I out. So we had a half in there, negative half cos 2t. Now, if we anti-differentiate sine 2, there'll be a plus c in there. Okay, and that's all in the I direction. Cool. And let's now do this next part. What's the antiderivative of cos? That's sine. So it'll be minus, I'll just leave a little gap, I learnt more or less in there, sine half t, and we're going to divide by half, and so that 2 will come out the front, and then we're going to have another different constant there, oops, j. Okay, so there's our two components here. Now we need to figure out what is c and what is d. How do we do that? We'll use our initial condition here, that r dot of 0 is equal to this. Okay, so in red, we know that r dot of 0 equals, so let's now substitute t is equal to 0. I'm going to do this quickly. Cos of 0 is 1, so that's going to be negative a half plus c I minus, when t is equal to 0, sine is equal to 0, and so we're just going to get minus dj. Okay, is that correct? Minus dj. Yep, that's fine. And we are told that this is equal to negative a half I. Okay, so if this is equal to negative half I, we just need to resolve each component. This tells us what? Well, here's the I component on this side, here's the I component on this side. They must be equal, so therefore C is equal to 0. C is equal to 0 in here. They must be equal. C is equal to 0. What's D equal to? Well, there's no J component on this side, so D is also equal to 0. So that's a boring response. And so what we get R of T, R dot of T is equal to, negative r cos 2t I minus 2 sine half t j. Good, halfway there. Let's go again. Therefore, r of t. How do we get from r dot t to r of t? Well, I missed things in here and here and here. Please forgive me. R dot t, we integrate again. Okay, so equals. Let's integrate this. Now, cos, when we integrate it, cos goes to sine, and so we're going to have negative. I'll leave a little gap there. We'll see what happens there. Sine 2t, and we're going to divide by 2, so it'll be minus 1/4 sine 2t. Perfect. And then we're going to have a new constant, so I'll CD E, and that's all in the I direction. Cool, and over here, sine goes to negative cos, so it'll be plus, I'll just leave that for a second, that 2, and it'll be cos half t, and we're going to divide by half, so that'll increase again, so it'll be plus 4 cos half t, and plus another integration constant plus f, all in the j direction. Again, we've been told that R0 is equal to 4j, so we can use that to find E and F. So therefore, I think I should be able to squeeze it in. R0 is equal to, when t is equal to 0, sine is equal to 0, and so we're going to get 0, so we're going to get EI, noise of a donkey, cos of 0 is equal to 1, and so that's plus 4 plus fj. Oh, that's really boring as well. Another trivial result. Okay, sorry about that. So equals, so r of 0 is equal to 4j from up here from our initial condition. So therefore, E is equal to 0, F is equal to 0. Boring. Anyway, there you go. So therefore, RT is equal to negative 1/4 sine 2ti plus 4 cos half tj. And there's your answer. Hope that makes sense. Sorry about the boring initial conditions up there, but that's how you do vector calculus.